Last section of the class. So 12.4 is normal distributions. So this idea of um, normal distributions, it's like specific rules that we have that something is normal, and then we have all these other rules that apply. So we have to decide if our data that we collected is normal, and if it is, then we can use some rules that we're going to learn about. So it's kind of a big objectives. Whoop, that's all of our objectives today. But let's look at these graphs I have down here. Okay. So this says the mean height for men in 1 billion BC was 4 feet 6 inches. The mean height for women was 4 foot 2 inches. Because of improvements in diet and medical care, the mean height for men is now 5 foot 10 inches and for women 5 foot 5 inches. Mean adult heights are expected to plateau by 2050. Suppose a researcher selects a random sample of 100 men, measure their heights, and construct a histogram for the data. So here are, um, let's see. So this is, aren't these all number of men, number of men? Yeah. I was like, I'm pretty sure they're all the same. So we're looking at a histogram. So remember what a histogram is. It looks like a bar graph, but it's not. It shows frequency. Now, I know a bar graph can also show frequency, but a bar graph, every bar is its own thing. And usually we want to use words for a bar graph. So it would be like, how many people have brown hair versus blonde hair, right? Those are words. You don't see words. This would be numbers, which they should have labeled, but it's just for this idea here. So what they're doing is they're saying, here's a histogram where we go up and over each bar is touching. And then here is the same histogram with more boxes, and it's leading into, so you're going skinnier and skinnier and skinnier. It's leading into this bell shape. So the first thing we look for when we want to see if our data set is normal is, does the histogram form a bell? Right? Basically, you want to be able to cut it in half and it be similar on both sides. So if the shape went up and down like this, that's going to be right skewed. It's not a, it goes up in a bell, but it's going to keep going out, right? In our boxes. If I have something like, each box is something like this, that's uniform. Everything's the same. Okay, you found like whatever your data was, everyone had the same answer or similar. So bell shape starts low, goes high, goes back down. So that's huge. The other thing that you would have in common when you have this bell shape is that the mean would be in the middle, and the median, and the mode. Now, mode is unreliable because you could have no mode. So we here, when we say normal distribution, we're looking for a symmetrical, right? Or bell-shaped symmetrical graph of our histogram. And we're looking for the mean, median, mode are equal or close, right? So if we're talking heights and the mean is, of women is 5 foot 5 and 1 inch, and the median is 5 foot 5. Pretty similar. It'd be way different if one's 5 foot 5 and one's 5 foot 7. That's not similar. 2 inches is a lot. So we're looking for these two things. Circle them, whatever you need to do, highlight them. This is, oh, it's not highlighting. This is really important here. Mean, median, mode are the same, and you're bell shaped. And that it's on a histogram. Histogram. And now Excel will make a histogram, and truly that's in the last year or so that a histogram was even possible in Excel, which was weird to me, because it's one of the main graphs of statistics and Excel wouldn't do it. But StatCrunch, if you go to stats, it's a software like just a calculator. It will make a histogram for you as well. Otherwise, you have to hand draw them. Okay. All right. So no matter what our bell shape is more flat or more skinny, the mean's always in the middle. And here starts to be the rules. So I say, is it normal? Collected my data, and I collected my data in a great way, right? I collected a lot of data and I collected it in some kind of random way. Okay. And once I have that good data and I know it's normal, then I can use the 68, 95, 97, 99.7 rule. Oops, I thought I was on this rule right here. And what that says is you always have the mean in the middle. Okay. That's the mean. I'm going to write that on here too. Oh, it is on there. The mean's in the middle. Okay. So the mean's right here. Um, and then if you add and subtract one standard deviation, so you're within one standard deviation in both directions. So one standard deviation in both directions, that will pick up 68% of your data every single time with normal. So grades are typically distributed normally. The mean's in the middle, you got people above, people below, just the way grades are. So in most classes, not all, sometimes you have a class that everyone's in the A's and B's. So occasionally you have that, or occasionally you have a lot more F's. So it just depends. So if we look at this, we would have our average right in the middle, and then everybody else would be within that one standard deviation. So you're literally going to take the mean, add the standard deviation one way, and subtract it the other. Okay, that's 68% of our data. Now, I want to be more accurate than 68%. I can go out 2 standard deviations, and I've now picked up 95. Then you go out 3, and you've picked up pretty much everything, right? Sometimes there's going to be, it's 99.7, so there's a slight chance. So if you want to pretty much know within everybody what numbers they're within for their grade, I mean, you could just say the range, but in this context, we could go out 3 standard deviations. So we take the mean, add, subtract, which we'll do on this next example. So memorize these. Write them on your note sheet. I let you have notes for the final and the next exam. So write those down. One standard deviation is 68%. Okay, so male adult heights in North America are approximately normally distributed with a mean of 70 and a standard deviation of 4. Find the height that is 2 standard deviations above the mean. So I'm going to go a little further, and we're going to draw our bell shape. And this is probably the easiest way to do this every time. That's not the best bell, but oh well. What goes in the middle? The mean. What is our mean? 70. Okay, I'm going to go 1 standard deviation up, and that is going to be to add the 4, and I'd get 74. I'm going to go 1 standard deviation below, and that's to subtract 4. So I would get 66. Okay, so how much of our data is between 66 and 74? 68%. That's not what the question asks, but I'm just asking, right? So it says find the height that is 2 standard deviations above the mean. So we want to go up 2 standard deviations. So add another 4, and I get 78. So this is what the question's asking. Find the height that is 2 standard deviations above, 78 inches. So 72 inches is 6 foot. So that's 6 foot 6. Ooh, that's tall. So that is 2 standard deviations above. That's really high. Do you guys remember, like in elementary school, you would get your standardized testing and you would have the standard deviations and all this kind of stuff on there? That's a place that I see it quite a bit for my children as well. Like, just so you know where your kid is in the realm, right? If your child is 78 inches tall, they are 2 standard deviations away from the mean. That is a lot. Okay, that's pretty good. It's on the border of what some statisticians say is significantly tall. Okay, it's on the border. Anything above would definitely be significantly tall. So I think 2 standard deviations is what most books say is considered significantly like it's big. And if we went short-wise, right, then 60, if we went the other way, subtract 4 more, 62. What is 62 divided by, why can't I think of that, divided by 12? 5 foot, what, 2 inches? Yeah, 5 foot 2 inches. Ooh, that's pretty short, right? That would be significantly short for a man based on this information. Okay, use the diagram or the distribution, excuse me, of male adult heights in the figure to find the percent of men in North America with heights 66 to 74. So it just wants you to say what percent, okay? So if I'm looking at between 66 and 74, 66 and 74, how many standard deviations is that? 1. So what percent is related to that? 68%. Okay. Normally you wouldn't have this on there for you. B. How many are between 70 and 74? Okay, right here, right? Well, isn't that half of 68? Right? So 34. So this would be 34%. So if I know the whole thing is 68, I can say, you know, that's 34%. Okay, what percent is above 78? So that's the one we were looking at before. We know that's significantly high, and that one is at 95. So you have 5% left for both sides. So you have 5% left for here and here. So what is half of 5%? Because you got half on each side. It's about 2.5%. Okay, so you can kind of use a puzzle to kind of add in more information. And what does the mean do? The mean splits it in half. So sometimes you have that asked about half. Okay. Female adult heights in North America are approximately normally distributed with a mean of 65 and standard deviation of 3.5. Find the height that is. I'm going to draw this. That's just what I suggest every time. Draw it. The mean is in the 65, and we're going to add the 3.5 so we can get 1 standard deviation above, excuse me, 68.5. And then I'm going to add 3.5 again, and that would be 2 standard deviations above, which is 72. And just in case we need it, we can add the 3.5 again and get 75.5. Man, that's a tall woman. Then we have to go the other direction, right? So 65 minus 3.5 is 61.5. Okay, minus 3.5, and I get 58. Okay, minus 3.5, and I get 54.5. Cool. Okay, now let's answer our questions. 3 standard deviations above the mean. Well, 1, 2, 3, 75.5. Very significantly tall. You're above the 2 mark because you are in the 3 mark. That is really tall. 2 standard deviations below the mean. So 1, 2 is 50. Is that 50? 8. I can't read my own writing. So 58. I had to minus it again in my head. I was like, okay, so you can answer questions. 68% is between what 2 numbers? You can answer 99.7 is between what 2 numbers? You could answer, you know, most women are shorter than 65. Okay, so and 65 is 5'3", right? 3 inches. Nope, 5'4". Nope, 5'5". Really? 5 divided by 12 is yeah. So 5'5". So I wonder if that really is the average. And then I am 1 standard deviation above. I've always considered myself slightly tall, but I'm only 1 standard deviation above. There's got to be women way taller than me. Okay, so along the same lines is something called a Z-score. Okay, and what this does is it describes how many standard deviations away a data item is. So what if you're right at like, my height is like right at 62.2? Like, I don't know, like you don't know the exact. The z-score is a way to find that. So let's scroll down. Here's how we're going to find the z-score. It is whatever you're given, the data, your data item, so it would be my height, minus the mean divided by the standard deviations. And this will tell you how many standard deviations away from the mean you are. And under the middle, you will be negative. So you'll know you're lower than the standard deviation, or excuse me, lower than the middle if it's negative. If you're higher than the middle, then you're, it's positive. So let's look at some examples of using the z-score. So the mean weight of newborns is 7 pounds. So I have to have the mean. The standard deviation is 0.8 pound. The weight of newborn infants is normally distributed. Again, these are rules for only normally distributed data. Find the z-score of a 9-pound baby. Oh, that's a big baby. So we would take 9. We would really want that to be a pen. 9, and we would subtract the mean. The mean is 7, and we divide by the standard deviation. So we're going to subtract the mean. Oops, I'm going to do it with the calculator. 9 minus 7, and then divide by the 0.8, and I get 2.5. A 9-pound baby is 2.5 standard deviations above the mean. That is a big baby, right? That's considered significantly big because it's above 2 standard deviations. Okay, let's do a little baby. 6 minus 7 divided by 0.8. So 6 pounds minus 7 divided by the 0.8, and I get negative 1.25. So that baby is in the negative, meaning it's below the mean by 1.25 standard deviations. So not considered significantly low because it's only 1.25 and you want to be lower than 2, but still pretty low. Okay, that's still not a big baby. So 7-pound baby. Well, the mean is 7. So when I take 0 and divide it by anything, I have 0. So when you get a z-score of 0, you are not away from the mean. You are at the average, right? Z-score is standard deviations away from the mean. So 0 is you're right here in the middle. Right here in the middle. You're not away from the mean. So this can really help if you want to know how far away you are from everybody else. So you need a mean and a standard deviation, and you can do it. Okay, so I think that's really all. Oh, no, I have one other idea. That's really most of this lesson. Okay. That's just more z-score. I think I'm going to skip that. Intelligent quotes. I think the rest of it. So I took this note packet from a friend. Pull margin of error. I don't even think I think I cut out some of this. So margin of error, if you're asked for it, you're going to do 1 divided by the square root of how many data you have. And what the margin of error does for me is it tells me how much error I'm going to possibly have based on the number of samples. So there's always going to be error because you're not going to have a perfect sample, and or you're not going to do not everything's perfect. That's how stats is, right? So this helps us calculate based on the number of samples. So if I only ask 5 people if they like math, it's not gonna be a real good sample versus 200 people. So my margin of error for 5 people versus 200 is different. And that's what this tells us here, is the margin of error. That one's skewed to the right, and we could be skewed to the left if the tail goes to the left. You'll learn about that in stats if you have to take it. And this is just taking quartiles, but I like a box plot for quartiles, and that's what we learn in stats the most is um, really the quartiles. The box plot shows quartiles as well. That's it. This does too. This is just saying, you could break up the data into quartiles and figure out where people are, but I'm not loving this as much as I want you to focus on. Is your data normal, bell-shaped, mean, median, mean, mode are the same? And then I want you to focus on the 68, 95, and 97 point, whatever, 99.7 rules. And then I want you to focus on the Z-score. Okay, that's it.